Fundamental Manufacturing Processes video series, examining the tools and techniques of manufacturing. This program explores the fundamentals of rapid prototyping. Rapid prototyping is a general term encompassing a variety of systems used to create three-dimensional physical models directly from electronic data. These rapid prototyping systems primarily create models using a layer-by-layer or additive means of construction. More recently, though, systems using a combination of additive and subtractive layering and pattern-based rapid prototyping processes have developed. The rapid prototyping industry began with the development of the first rapid prototyping technology in the mid-1980s. Rapid prototyping technologies are based on the solid modeling portion of computer-aided design, or CAD. Solid modeling involves using CAD model data to fully describe a part shape, including its interior volume and outside surfaces. Rapid prototyping systems use this solid modeling data to build fabrications layer by layer in extremely thin cross-sections. These cross-sections, or slices, are stacked one atop another in succession until the shape is complete. This permits manufacture of intricate and complex shapes and surfaces much more simply than by conventional methods. Rapid prototyping technologies can also produce models using scan data generated from the three-dimensional digitizing of existing parts and medical imaging devices. The materials used for producing prototypes rapidly are broadly classified as either liquid, powder, filament, or foil. Typically, rapid prototyping systems operate untended. Upon completion, some post-processing, such as surface finishing or support removal, can be required. The net result of rapid prototyping, though, is a marked reduction in fabrication time and cost of models. Although rapid prototyping technologies were initially developed to create physical models for design approval and part verification, many other technological applications have emerged, such as the creation of rapid tooling for molding processes, low-volume parts production, the manufacture of patterns for casting, the production of functional prototypes, and more. Rapid prototyping systems range from large modelers suitable for shop floor and laboratory environments to smaller desktop modelers. Within this range, there are numerous rapid prototyping technologies and systems, with the primary types including stereolithography, selective laser sintering, fused deposition modeling, ultrasonic consolidation, the ProMetal system, the Thermojet modeler, the 612 modeler, the Z810 modeler, the Eden 330 modeler, and room temperature vulcanized tooling. Stereolithography, first of the rapid prototyping technologies, is a liquid-based process for making models. The models are built in layers within a reservoir of a liquid, thermosetting epoxy-based photosensitive polymer by selective curing with the ultraviolet light from a focused low-power laser beam. The laser beam continuously traces and selectively hardens the thin layer of polymer according to the CAD file. Once tracing of the layer is complete, the platform that the model is built on moves down precisely one layer. Liquid resin is then dispensed over the model, and tracing of the next layer begins. Minimum layer or slice thickness ranges from 1/1000th of an inch to 12/1000ths of an inch. Supporting ribs for overhangs and undercuts are built up along with the model and later removed by secondary operations. When the model is complete, the platform rises out of the polymer reservoir. Once the excess polymer drains away, the model is removed for post-processing, such as removal of supports, additional curing, and surface finishing. Stereolithography machines can produce models as large as 40 by 32 by 23 inches. Additionally, multiple smaller models or model components can be nested together for simultaneous building. Models made by stereolithography can be extremely precise, with thin and sharp features and smooth finishes. Substantial post-processing may be required, however, to separate the model from its supports. Additionally, polymer cost is high. Selective laser sintering is somewhat similar to stereolithography, except that the materials used to form models are in powder form, and the laser is a more powerful carbon dioxide unit. A layer of powder is deposited over the machine build area and spread evenly by a roller. Powder layer thickness ranges from 0.003 of an inch to 0.12 of an inch. The laser beam scans the model design according to the CAD file and selectively sinters or fuses the powder particles together. The model platform lowers incrementally as each successive layer of powder is similarly fused. Once complete, the model or models are moved from the machine in a cake of unsintered powder. They are then manually removed from the powder cake and finished using secondary operations. Typically, the excess powder is recycled for reuse. The principal advantage of the selective laser sintering process is the wide range of materials from which models can be created. Among the assortment of suitable materials are polycarbonate, acrylic styrene, nylon, thermoplastic elastomer, investment casting wax, silica, and zirconium silicate foundry sands, and even polymer-coated carbon steel. However, maintenance and operating costs are high. Selective laser sintering machines can produce model designs as large as 14.5 by 12.5 by 17.5 inches. Fused deposition modeling involves feeding a thermoplastic filament into a heated extrusion head that moves in the X and Y axes. The heated extrusion head melts and deposits the thermoplastic material on a table that moves in the Z-axis, building the model. The molten thermoplastic is channeled through an extrusion tip, which reduces it to a fine bead for deposition onto a substrate material. After depositing each bead, the tip flattens it in preparation for subsequent layers, and the model is built up layer by layer. Layer thickness is typically between 0.005 of an inch to 0.13 of an inch. As it is deposited, the molten thermoplastic material is just slightly above its melting point. Solidification occurs immediately after extrusion, as the material cold welds to previous layers. The most common material used for fused deposition modeling is acrylonitrobutadiene styrene, or ABS thermoplastic, in various colors. ABS provides tensile strengths of up to 5,400 pounds per square inch. Other materials used include investment casting wax, elastomer, polycarbonate, and polyphenol sulfone. Depending on the machine, maximum part size can range from 8 by 8 by 12 inches on the smallest machine to 24 by 20 by 24 inches on the largest machine. Fused deposition modeling is moderate to fast in building speed. Additionally, most systems incorporate a water-soluble support material, which aids in support removal. The strength and heat resistance of models are also advantageous, and the variety of colors available are useful in accentuating part features. Ultrasonic consolidation produces direct metal parts from CAD data by ultrasonically welding layers of coiled aluminum foil strips to a prepared metal substrate. As the foil strips are placed on the substrate, a tool called the sonotrode uses high-frequency vibratory energy and moderate force to disrupt the interface surfaces, inducing interatomic attraction and metallurgical bonding between the foil and the substrate surfaces. Once ultrasonically welded, the layer is then milled to the cross-sectional shape defined by the CAD data. This process of adding material to a previous layer and then removing the excess continues until the part is complete. Like other rapid prototyping processes, ultrasonic consolidation also allows for the buildup of complex geometries, overhangs, and enclosures within a part. Ultrasonic consolidation can be used to bond a variety of similar and dissimilar metals, as well as certain ceramic metal combinations. The Pro Metal System modelers are also used for creating metal models. This system involves using inkjets to apply a liquid polymeric binder onto powder media to produce models. The models are built from steel-based powder from the bottom up. Upon completion, models are sintered to remove the binder and bond the powder particles, and then infiltrated with bronze to substantially reduce or eliminate porosity. Besides the capability of making high-strength, durable models, no support structures are required. Tooling for plastic molding processes are a common application. Of the smaller rapid prototyping systems, the Thermojet, 612, Z810, and Eden 330 modelers are all inkjet-based. The Thermojet modeler is a multi-jet modeling system that uses an array of over 300 jets to produce wax models as large as 10 by 7.5 by 8 inches. The Thermojet modeler is a self-contained compact unit which is equipped with a cartridge system for easy loading of the modeling material. Post-processing of Thermojet-produced models is minimal. The 612 modeler uses 2 print heads, one to build up models using a proprietary thermoplastic, and the other to build up supports using a proprietary wax. These supports are designed to dissolve in solvents without damaging the model material. The 612 can produce models up to 12 by 6 by 6 inches. Layer thickness can be as thin as 5/10,000ths of an inch. To ensure precise layer thickness, a milling operation is performed between layer buildup. This is carried out until model completion. The 612 system primarily produces small, highly accurate detailed patterns in the range of plus or minus 1/1000th of an inch. The system is commonly used to provide models for the medical and jewelry industries. The Z810 modeler is among the fastest rapid prototyping systems, having a building speed of 1 to 2 inches per hour. The Z810 modeler uses one of 2 powder material types to build models. The first combines starch and cellulose, and the second is plaster-based. Both materials can be subsequently infiltrated with wax or particular resins to enhance certain qualities. The Z810 modeler has a wiper blade that smooths the powder in the build area until it is level. Once level, the powder is infiltrated with a binder from the printer head. The binder is dispensed only in the areas dictated by the CAD file. Once a layer is printed, the platform lowers and the existing layer is leveled over with powder. And printing resumes. This process is repeated until the model is complete. The Z810 modeler can build models up to 20 by 24 by 16 inches. Models produced tend to have rough surface finishes, but low cost, low power usage, inexpensive materials, and reuse of unused building material are key advantages. The Eden 330 modeling system features 8 heads that contain a total of 1,536 nozzles. Half of these nozzles jet fine droplets of a proprietary photopolymer model material, and the other half droplets of a proprietary photopolymer support material. This system produces extremely thin layers of 6/10,000ths of an inch. Producing such thin layers increases detail, accuracy, and finish smoothness of the models. Each model layer is cured immediately by exposure to ultraviolet light. Then the build platform descends and the inkjet unit deposits the material for the next layer. Upon model completion, the gel-like proprietary support material is easily removed. A rapid means of producing soft tooling for low-pressure molding involves the use of room-temperature vulcanized or RTV silicone materials. These RTV silicones are the preferred materials since they do not require special equipment for curing. In general, RTV tooling production begins by using a prepared rapid prototyped model as a pattern. Development of the first mold half begins by securing the pattern in oil-based clay or other building materials and constructing the parting line. Once done, the pattern is then secured in a box or frame. Silicone RTV molding material is then poured around the pattern and allowed to cure. Typically, it is necessary to apply a vacuum to either the RTV molding material before pouring or the tooling assembly after pouring to remove air bubbles from the molding material during curing. Once the silicone has cured, the box is removed, and the mold half and pattern are prepared for the pouring of the second mold half. This preparation can include a release agent coating to ensure separation of the mold halves, and the inclusion of a gate for injection, and venting to allow air in the mold to escape during the injection. Once prepared, the second mold half is poured and allowed to cure. Once entirely cured, the mold halves are separated along the parting line. The pattern is removed and the mold is prepared for use. RTV tooling can be used to mold small to medium quantities of parts out of a large variety of urethane, epoxy, or other polymer materials. RTV tooling can typically be used to mold several parts before replacement becomes necessary. The number of parts produced depends on accuracy and finish requirements and the complexity of the part geometry. Dozens of simple parts can be produced from a single silicone rubber mold, but 10 to 20 is typical if the parts are more complex. Wear of the mold occurs due to the exothermic and reactive nature of the molding materials, and because of the necessity to mechanically deform the mold to remove parts. Let's review the material contained in this program. Rapid prototyping is a general term encompassing a variety of systems used to create three-dimensional physical models directly from electronic data. These rapid prototyping systems primarily create models using a layer-by-layer or additive means of construction. More recently, though, systems using a combination of additive and subtractive layering and pattern-based rapid prototyping processes have developed. Rapid prototyping technologies are based on the solid modeling portion of computer-aided design, or CAD. Rapid prototyping systems use solid modeling data to build fabrications layer by layer in extremely thin cross-sections. These cross-sections, or slices, are stacked one atop another in succession until the shape is complete. This permits manufacture of intricate and complex shapes and surfaces much more simply than by conventional methods. Rapid prototyping technologies can also produce models using scan data generated from the three-dimensional digitizing of existing parts and medical imaging devices. The materials used for producing prototypes rapidly are broadly classified as either liquid, powder, filament, or foil. Although rapid prototyping technologies were initially developed to create physical models for design approval and part verification, many other technological applications have emerged, such as the creation of rapid tooling for molding processes, low-volume parts production, the manufacture of patterns for casting, the production of functional prototypes, and more. Rapid prototyping systems range from large modelers suitable for shop floor and laboratory environments to smaller desktop modelers. Within this range, there are numerous rapid prototyping technologies and systems, with the primary types including stereolithography, selective laser sintering, fused deposition modeling, ultrasonic consolidation, the ProMetal system, the Thermojet modeler, the 612 modeler, the Z810 modeler, the Eden 330 modeler, and room temperature vulcanized tooling.